Hey folks, in this lesson I want to talk with you for a few minutes about two really important, really foundational concepts for what we're going to be doing in this part of physics as well as all of physics throughout the year. And these are terms you've heard before. They're concepts that you've spent some time studying before, but we'll spend a little bit more time talking about them in depth, hopefully add some details you didn't know before, and then clear up any misunderstandings that you may have about that. And really what we're looking at here is this idea. We're looking at the concepts of speed and velocity. So we're going to define, explain, and distinguish between the ideas of speed and velocity. As we start, take a look at this basketball. And I want you to look at that basketball carefully. And my question is simply, is this ball moving? Watch it carefully for a few more seconds. And again, the question is this ball moving? Is it getting closer to you? Is it getting further from you? Is it changing? Is it moving to the right or left of the screen, getting closer or further away from either side or the top or the bottom? Again, is this ball moving? Because some of you could make a very good case for the fact that this ball is absolutely not moving. It's not going anywhere. However, some of you might try to make a pretty good case for the fact this ball is moving and it's zooming along at maybe hundreds of thousands of kilometers per hour or something like that. So which is it? Is the ball moving or not? Well, turns out it's not really a fair question. And here's the reason it's not a fair question. And that is because of this statement that motion is relative. Now, what do we mean by that motion is relative? Well, what we see depends on from where we see it. What we observe in terms of motion depends on where we are looking at it from, or from where we're looking at it, excuse me. Things are going to look very different depending on our motion in comparison to the motion of the thing being observed. For example, we have this toy car here and this little boy with the ice cream cone. And if we watch what happens, we might say that the car moves towards the boy. Is that a true statement? Well, of course it is. The car moved towards the boy. At the same time, we might observe the same motion and we might say that the boy moves towards the car. Well, which is it? Does the boy move towards the car or the car towards the boy? Well, both are correct. Because what we're talking about is in relationship to. How do they move in relationship to each other? Or, to complicate things even more, we might say that they both move, which again could also be true in relationship or relative to each other. And so, what's the main point here? Well, before we can actually get to that, there's another term that comes to mind, and that is the idea of frame of reference. What do we mean by frame of reference? Frame of reference is simply the location or the position from where motion is observed, the place that we're going to see the motion from. And usually this position is where we're going to define at rest, or the sitting still point. This is the place that we're going to define the motion relative to or in comparison to. It's the thing that is sitting still, if you will. And we call that place the frame of reference. It is the thing that we're using to compare our motion to. So from here on out, and this is kind of the capture, everything we've said so far, from here on out, unless we say otherwise, our frame of reference is going to be the Earth. We are going to look at all of our motion relative to the Earth. If this was an astronomy class, that might not be the case. We might be looking at our motion, say, relative to the sun. Going back to our previous example then, say in comparison to or relative to the sun, is the basketball moving? Well, of course it is. It's on the Earth, and the Earth is moving around the sun. And so therefore the basketball is zooming around the sun at thousands of kilometers per hour. However, if you're even looking at a bigger picture of astronomy, of course our sun is moving in comparison to other things, and so it all changes depending on what our frame of reference is, what we are comparing it to. But again, for our class, for this study in this class, we're going to assume that our frame of reference is the Earth, that the Earth is sitting still and we're looking at motion in comparison to the Earth. And so you need to make that assumption from here on out. And making that assumption, of course, if I was to ask you, is our basketball in the previous slide moving? Your definitive answer would be, that's correct. It would be no. The basketball is not moving in comparison to the Earth. Moving on then. The next thing we need to talk about is the idea of speed. And I'm sure you've heard of speed before. This is nothing new. This is a concept you've covered before. And as I'm sure you know, speed could be defined as a measure of how fast something is moving. And when we talk about how fast something is moving, what we're really referring to is the distance it travels in some period of time. How far does it go, and how long does it take to go that far? That would be how we'd measure the speed. We could somehow measure the distance it travels, and we could use some sort of a timing device to measure the time. We would divide those, and that would give us the speed, the distance divided by the time. We could put that in terms of an equation. Here would be our very first equation for the year, a very simple equation, again, an equation you've had before. And the equation is simply S equals D divided by T. Speed equals distance divided by time. By the way, in the notes, typically when I have an equation that's important, I'll put it in a box like this for you. I'll highlight it. And this could be our very first equation. Again, not a new equation, not an equation you haven't seen before or a relationship you haven't worked with, I'm quite sure. But the first equation for our study for this year. Speed is distance divided by time. Now, before we go any further, we need to make a careful distinction, especially for this unit and for this particular course. We need to make a distinction between the idea of distance and displacement. So let's talk about that for a minute. Distance is defined as how far an object goes. You could measure it with a tape measure. You could measure it with a wheel that I'm sure you've seen before that would track off a distance. You'd simply put the wheel on the ground and let it roll. And at the end, you'd look at the dial and it would tell you how far you traveled. That would be distance. Compare that to the idea of displacement. Displacement is defined as how far an object is from where it started. When you finish, where are you from the position from where you started? How far are you when you're done from where you started? Not the total amount of feet, meters, whatever you've traveled, but simply where are you from where you started. So for example, let's say a person leaves his house and he walks 20 meters out to his mailbox. He then turns around and walks back 20 meters to his house. What would be the distance he traveled? Well, the distance he traveled would simply be 20 meters out and an additional 20 meters back, or he's traveled a total distance of 40 meters. But that's different for displacement. The total displacement he's traveled is simply 0 meters. He is at exactly the same place he started from, and so he's nowhere from the position from which he started. His displacement would be 0 meters. The two are very different in this case. They're not always different. Many times they are exactly the same, distance and displacement, but sometimes they're significantly different. So what's the difference, or when are they different? Well, displacement takes into account the direction in which the motion occurs, where the distance only deals with how far the object travels. Okay. So given that, now we can move on to talk about our next topic, velocity, which I'm sure you've heard of before. And in many ways, or in kind of common language, speed and velocity are used interchangeably. Well, it turns out that many times that's okay to use them interchangeably. Many times they do mean very much the same thing. However, in physics, there can be a difference between speed and velocity. So we need to carefully look at that and see what the differences may be. Velocity is technically defined as an object's speed in a given direction. And therefore you can see the difference. It's not just how fast it's going or the speed, but in a given or a particular direction. For example, 60 kilometers per hour is a speed. 60 kilometers per hour to the north is a velocity. In the second example, we've given a direction. Therefore, we've really specified the velocity, not just how fast. So in terms of an equation, here could be an equation for velocity. The equation looks very much the same, distance divided by time, or d over t. We put a v here, of course, for velocity instead of speed, and then the distinction in a particular or in a given direction. Velocity is distance divided by time in some direction. Now, in addition to that, velocity can also be defined as the displacement of an object over some period of time, keeping in mind the difference here now between the idea of displacement and distance. Remember, displacement involves direction, or when direction matters, displacement comes into play. So we could write another equation, very similar equation, written just a slightly different way. Velocity is equal to displacement divided by time. Again, because displacement incorporates the idea of direction. So let's say we have a bike that travels 10 meters up the street, 100 meters up the street, and then it turns and travels back down the street 20 meters, and it takes a time of 60 seconds to make that total trip. Well, the speed of the bike could be defined or calculated in the following way. Distance traveled divided by time. It travels 100 meters up the street. It travels 20 meters back down the street, of course, in 60 seconds. Traveling a total distance now of 120 meters in 60 seconds. And of course, 120 meters divided by 60 seconds would give us 2 meters per second for our final speed. By the way here, notice what's called the dimensional analysis. We talked about that, or you read about that in chapter 1. And dimensional analysis simply means we've included the units in our work. We've carried them through, haven't just tacked them on at the end or haven't forgotten about them altogether, but we've done the math with the units. And that's important. That's called dimensional analysis, and we'll talk more about that in the future. Main point here, though, is the idea of speed. Total distance divided by time. 120 divided by 60 for a speed of 2 meters per second. Now, let's look at the velocity of our object, or of our car, I guess, or bike traveling up the street, Velocity is displacement divided by the time interval. In other words, how far is the bike when it stops from where it started? Where is it from where it started? Well, if it goes 100 meters up the street and 20 meters back down the street, it's only 80 meters from where it started. Time interval is still 60 seconds. It took 60 seconds for that to happen. 80 meters divided by 60 seconds gives us a velocity now of 1.3 meters per second, which is very different than our speed being 2 meters per second during this trip, our velocity only being 1.3, again, because our velocity involves or takes into account direction. So when direction matters, or when the direction is a factor, the speed of an object is different than its velocity. If the direction doesn't matter, or the direction doesn't change, if it's a consistent direction, then the speed and the velocity will be exactly the same. Differences between speed and velocity. Many times very much the same idea with some important distinctions. Another topic we need to talk about briefly is the idea of average velocity versus instantaneous velocity. Now I want to mention here, and I don't think it shows up on the PowerPoint, the conversation we're going to have here about average velocity versus instantaneous velocity is very similar to the conversation you could have, or the discussion you could have, of average speed versus instantaneous speed. We're just going to talk about it for right now in terms of velocity, but the same argument goes for speed, as we'll talk about here for velocity. So what is average velocity compared to instantaneous velocity? Well, the difference is all about the time interval. How long does this take? Average velocity is a displacement of some object over some measurable amount of time, a time where the velocity actually might change, where it might vary. Time has to be somewhat significant that the velocity could actually change. Compare that to the idea of the instantaneous velocity. When you see the word instantaneous, and notice my emphasis there on the first part of that word, instantaneous refers to the velocity of an object at an instant. That's the word instantaneous speed, usually pronounced instantaneous, of course. An instant is a single moment of time, so small, in fact, that the velocity could not change during that time. Now, it's not zero time, because if it's zero time, then nothing can occur, of course. It is still an amount of time, but it's such a small period of time that it's impossible for the velocity to change. Instantaneous velocity is the speed, is the velocity at a moment in time, as opposed to some measurable period of time, which would be the average velocity. A subtle difference, but a really important difference between these two types of velocity. So to determine the average velocity of your car, you could simply measure the displacement, use maybe the odometer or some other device to measure the total distance, the displacement the car would travel in some period of time. Maybe use a stopwatch or whatever else to measure that time. And then you could divide that by the time to get the average velocity. The instantaneous velocity of your car, however, could be measured by the speedometer at that moment. You could not use the speedometer to measure your average velocity because it doesn't tell you your speed over some long period of time, or your velocity over some long period of time, It tells you your velocity at that instant, at the instant you look at the speedometer. So the speedometer would give us a value for your instantaneous speed, not your average. You'd have to do your average velocity a different way. And hopefully that helps distinguish between these two, again, very closely related subjects, but slightly different. And again, it's all about the time interval. So a question for you. Does a policeman's radar gun measure my car's average or instantaneous speed? Traveling through Hampton Ridge, I'm on Henderson Road, and I'm flying along at 45 miles per hour, let's say. And the policeman's radar gun hits my car, and he gets a display on his radar gun, tells how fast I'm going. Does that give my average or my instantaneous? Well, of course, unfortunately, it gives my instantaneous speed. It gives the speed of my car at the moment that radar signal hits my car. It would be nice if it gave the average speed, because chances are over the last half hour or so, my average speed would have been less than the speed at which I was traveling when the radar gun hit, and I wouldn't be faced with a ticket or a fine or just a stern conversation with the police officer. No, but that's not the case. The radar gun measures the speed at the instant that radar signal hits my car and doesn't really care how fast I'm going a couple seconds later after I slam on the brakes or even a few minutes before that. Hopefully, again, that helps illustrate the idea that, or the difference, the distinction between average velocity and instantaneous velocity. It measures the instantaneous velocity. So again, the difference here, the distinction, is all about the time interval. Another way to think about the idea of instantaneous velocity is this mathematical concept called a limit. Instantaneous velocity can be defined as the limit as the time interval, sometimes written as delta t, delta meaning change in, or the time interval. The limit as the time interval approaches zero, very, very, very small, infinitesimally small, as a matter of fact, period of time, of the displacement over that very small time interval. The idea of limit here is used to express the idea of instantaneous velocity. Very small, again, infinitesimally small period of time. That whole idea of limit is very helpful in defining or describing this idea of instantaneous velocity. Okay, now last issue or last thing we need to talk about in this particular lesson is the idea of units. Whether we are measuring velocity or speed, whenever we measure anything in physics, we need to have units. We need to tell what it is we're measuring it in. What are the values that we're using to measure it? And it turns out they're the same, whether we're measuring speed or velocity. The units are exactly the same. The units for speed and velocity are anything that measures distance or displacement and anything that measures time. There is not one set of units or one particular unit for speed and velocity. There can be a variety of different units. Anything that measures distance or displacement over anything that measures time. It really depends on what it is we're measuring or what it is we're studying. For example, one unit of speed and velocity would be meters per second. We're going to use meters to measure the distance. We're going to use seconds to measure the time. And that's a quite acceptable and a very widely used unit of speed and velocity, meters per second. We'll use that quite a bit. That might be measuring the speed of somebody running on the track, or the speed of something that's thrown or shot or something like that, and kind of a medium range speed or velocity, if you will, meters per second, a very common unit, excuse me, of speed and velocity. One that we probably won't use a whole lot, but it would surely be acceptable, would be the idea of centimeters per minute. Of course, this would be a unit that would be used for a very slow moving object. It's not going to move very far in a pretty big period of time. A minute, of course, compared to a second, quite a bit larger. But nonetheless, centimeters per minute would be a very acceptable unit for speed or velocity. One we will use quite a bit, that we've alluded to even a little bit today, is the idea of kilometers per hour. This might be the unit of speed for a vehicle. Distance in kilometers, time in hours, kilometers per hour. Again, another very acceptable and quite appropriate unit for speed or velocity. Last thing I want to mention to you, remind you, one, you might want to look at sections 1 through 3 of chapter 2, the next chapter in your book. Kind of reviews the same things we just talked about in very much the same terms. Just another way for you to get your hand around, get your hands around these topics. Chapter 2, sections 1 to 3. Highly encourage you to read through those and go back and kind of study it in that way. And then, of course, for next class, make sure you bring your 2 C-cell batteries. You need 2 batteries per group, so 2 batteries for every 2 people. If you're not sure who you're working with, or you weren't able to partner up with somebody, try to bring in 2 batteries. It's better to have a couple extra than it is to not have enough. Thanks, folks. See you soon.